This conference will now be recorded.
Okay, so welcome to the Wednesday Yaskawa IQ training class, and we're recording this one because this is the season and a lot of the guys are out early and in the field, which I completely understand. I will conduct a session today on very basic use of an oscilloscope. And an oscilloscope is not normally used, certainly not as frequently as a volt-ohm meter, which most of us carry around, but it is so much more of an important tool when we need it. And when you need it, you need it. The fact is that a volt-ohm meter will give us an instantaneous picture of a condition. You take a reading on a voltage, and it tells you what that voltage is as long as you are holding the leads onto the source. But there's no 5 seconds before, 5 seconds after. It's basically an instantaneous reading, and that has a certain use. But when you want to see a trend, when you want to see something over time, so not a piece of point data, but a waveform, then the tool to use is an oscilloscope. And an oscilloscope has great utility in analyzing some of the problems that we come up with in the field on variable frequency drives. It obviously is used for a whole bunch of other things, but this is a drives class, so we're going to talk about it relevant to troubleshooting drives. The oscilloscope is much more expensive than a digital volt-ohm meter, a DVM. But I will tell you that it's not that much more expensive, and when you need to troubleshoot something and you can't get the data that you need to solve the problem from your digital volt-ohm meter, all of a sudden the oscilloscope becomes very inexpensive. But you're going to run for a good field compatible, heavy duty, shock resistant, water resistant oscilloscope, and I use something called a fluke scope meter. So it's actually a meter, a digital volt-ohm meter, and an oscilloscope. You're looking around $3,000, and a digital volt-ohm meter, as you know, you can buy for a couple $100. So two totally different classes of instrumentation. Very tough to justify, but when you need it, you need it. So the oscilloscope is something that we use to look at waveforms over time so we can see trends that will tell us more about what we're trying to troubleshoot. It is, for example, something I would use to record overnight when I can't be there. You can set the oscilloscope up to record a waveform for, depending on your memory bank in the oscilloscope, and you can augment that with additional memory chips that you can plug into the oscilloscope, or plug the oscilloscope into a laptop and access the memory there. But you can record waveforms over time. So if there's something happening on the power grid and you can't convince the utility that it's happening, then the oscilloscope waveform is a great way to do it. The use of an oscilloscope in terms of variable frequency drives is dangerous, the same way a digital volt-ohm meter is dangerous. You have to understand how to connect the thing, and for the most part, you have to be sure that when you're using it, you are practicing the normal safety procedures of operating around high voltage. When you connect it to the output of a VFD, you're dealing with a 700 volt DC bus. If you connect it wrong, the worst, the least you're going to do is either blow up the oscilloscope or the VFD, and so you just spend a bunch of money. I certainly hope nobody would get hurt doing that, and that's one of the reasons why I caution you at this point. Be very careful, read the safety instructions. But just make sure you don't hook the thing up wrong. A general rule that I use when I hook up voltage probes to high voltage is don't connect to ground. If you can avoid connecting to ground and still get the signal that you want, that avoids a lot of sins that cause problems. But that's a general rule. Now, I'm going to show you, I'm moving the camera, and it's going to take a while for this thing to refocus, but this is the scope meter. You can see it's basically a big digital voltmeter. And to put some scale on it, there's my droid. So the droid's about as big as a voltometer. And so this is about twice as wide and about 1.5 times as long. This one happens to be the Fluke 190-204. Sorry, it's not focusing very well. Scope meter. This is the one that's about $3,000. Comes in a nice case. This is a probe, and you'll learn more about the probe as I play the videos. But the fact is that this is a tool that you need to understand to use, and once you do, it's going to become a lot more useful for you to do the troubleshooting. Troubleshooting is expensive. Let's bear that in mind. You're out in the field, you can't bill your job, the drive's not working. Those economic situations typically run up a bill that easily pays for the oscilloscope in one incidence. So the other thing that you can bear in mind is that when you do need to use an oscilloscope, you don't necessarily need to own one. You can always rent one. You can rent one for $80, $100 a day. So I'm going to start playing the first video on basic oscilloscope use, but I wanted you to keep a couple things in mind. The oscilloscope is basically a digital voltometer over time. It's taking hundreds, if not thousands, of digital voltometer readings and charting them for you. The display on an oscilloscope is basically an XY chart. So the oscilloscope is an automated way of doing this. Let's say you want to trend voltage over time, but you only have a digital voltometer. Your ability to take a reading and record it on a time base, so let's say you start a clock ticking, and in the first second you take a reading, and then in the second second you take a reading, and in the third second you take a reading, and then you write those down. And okay, I know you can't do that every second, but for the sake of this conversation, let's just say that you can. You've taken a reading on the voltage every second. Now you're going to put that on a piece of graph paper and you're going to chart it. And then you get a trend over however many seconds, however many readings you take. And now you can start to look at the voltage performance over time. The oscilloscope will do that for you, and instead of one time a second, it'll take point data readings. Well, my scope is 200 megahertz, so it'll do that 200 million times a second at the highest rating. And it'll automatically chart that for you in a nice graph on that screen of that oscilloscope. So it's a highly automated, extremely fast data collection device. And when you look at the buttons on the oscilloscope, don't become overwhelmed right away, because it's not that hard to use. There's zoom in, zoom out. They call it differently, but once you know that it's zoom in, zoom out, you know what to do with it. There's ways to move the graph up and down and sideways on the screen. And then about the most complicated thing that we're really going to need for what we want to do in terms of reading the VFD output signals and the signals from our sensors, etc., is to understand triggering. And triggering is when you tell the oscilloscope, don't do anything until this condition occurs. That's a trigger that tells the scope, okay, now take one reading, one cycle, and show it on the screen. So if I'm trying to capture a square wave, the square wave is first 0, then it rises. It has a rising edge up to the voltage. In the case of a 460 volt VFD, the output square wave is going to be around 700 volts. And then it turns off and the edge falls back to 0. So it looks like a rectangle. I can set the trigger point somewhere between 0 and 700 volts, and I can say leading edge, and it will capture one pulse and show it on the screen. And then I can say repeat, and it'll catch the next pulse. That's what triggering is about. And that's about as complicated as it's going to get for the first time use, first time class. But now you can read the output of a VFD and decide whether there's a problem or not. The ability, for example, to look at the shape of a sine wave going down to a submersible motor is very important. As my good friend Craig has found out and been educating us on, the waveform shape of the voltage going to the submersible motor has a great effect on how the submersible motor operates. So you can't see that with a digital voltometer. You can't see waveforms. All you can see is point data. Oh, it's 460 volts. Oh, it's 230 volts. But the waveform can only be illustrated by an oscilloscope. So that hopefully puts it a little bit in context. I'm going to play this video for you now because they do a much better job than I do in terms of that, and then we'll come back.
An oscilloscope is another important tool when it comes to analyzing and debugging circuits. They let you see electrical signals, and you often hear it abbreviated as Oscope or sometimes just scope. They're particularly handy when it comes to measuring things like amplitude, frequency, and transient signals that your multimeter just can't catch. In older cathode ray oscilloscopes, the electrical signal under test changed the voltage between a set of vertical deflection plates that caused an electron beam to move up and down as it swept across a phosphorescent screen. But modern digital scopes take measurements using an analog to digital converter to sample the signal and then draw the waveform on a screen. While all these buttons and knobs may seem daunting at first, don't worry, I'll show you which ones you need to care about so you can begin taking measurements. To start, let's look at the user interface. The first thing you'll likely notice when looking at a scope is the display. This is where your waveform and any information about it will be drawn. Here we have two ports marked with colored bands that accept probes with B and C connectors. You'll commonly see scopes with 1, 2, or 4 channels. This one happens to have 2. The vertical section controls the voltage scale on the display for each channel independently. The horizontal section controls the time scale on the screen for both channels. You can manually adjust how the scope triggers with this section, which tells the scope to start measuring when it sees a particular part of a signal. The menu section contains various settings, some of which we'll use later, like saving an image. You'll also be pressing single, run, and stop quite often to start and stop measuring. As it turns out, scope probes are more than just some pieces of wire. The most common probes you'll find are passive voltage probes, which means that they measure the voltage difference between the ground clip and the tip of the probe. There are no active electronics in the probe, just some cable, resistors, and capacitors. If you were to look inside our oscilloscope, you would find that each of the input ports has a 1 megaohm resistor and a 16 picofarad capacitor connected in parallel from the signal input to ground. Just connecting wires to the port would work for low frequencies, but since they look like antennas, they're liable to pick up noise and inject it into our circuit or measurement. To fix that, we use a coaxial cable to provide extra shielding. Now, if you look at most scope probes, you'll see a little switch labeled 1x on one side and 10x on the other. This refers to the amount the probe attenuates the signal. If you switch it to 1x, it is exactly like our drawing. The tip is connected directly to the inner wire of the coax cable, and the ground clip is connected to the shielding. While this works well for signals with frequencies less than a few megahertz, coax cable can act like a capacitor and add more than 100 picofarads to your test circuit. This can adversely affect many circuits, especially if you're trying to capture higher frequencies. To remedy this, many probes have the option of enabling an inline 9 megaohm resistor to isolate your circuit from the cable. This is what the 10x setting on the probe does. The 9 megaohm resistor in the probe and the 1 megaohm resistor in the scope act as a 10-to-1 voltage divider. It's important to note that 10x does not mean 10 times gain. It means the signal is reduced by a factor of 10. The problem with adding a resistor in line with our signal is that with the capacitance in the coax and scope, it creates a low-pass filter, and high-frequency signals will appear smaller. To fix this, 10x probes include an adjustable capacitor in parallel with the 9 megaohm resistor used to compensate for the low-pass filter. This will keep the signal attenuation more or less the same across all frequencies. Now, I recommend leaving the probe on 10x as that's the best compromise between signal attenuation and having the probe affect the circuit you're trying to measure. However, that does mean we need to tell the oscilloscope that we're using a 10x probe, and we need to tune the compensation capacitor inside the probe. You'll likely only need to tune your probe once, but it's a good idea to check them every now and then to make sure that the compensation capacitor didn't get adjusted by your lab partner or some spooky ghosts. To start, select 10x setting on your probe and plug it into the oscilloscope. Turn on the scope and let it boot up. We'll need to make some initial changes to the settings. First, make sure channel 2 is off. Press the channel 1 button to see the input settings. Make sure you're on DC coupling as we want to see all parts of our signal. Press the button next to probe, highlight 10x using the top left knob, and press the knob to select it. Press the trigger menu button. Make sure type is set to edge and source is channel 1.
One thing I want to say is every scope has the buttons that he's talking about. They're just arranged differently. So don't worry about where the buttons are. Just understand the concept. What he's doing right now is he's going to hook this probe up to those 2 pins in the lower right-hand corner of his scope. My pins for that setup are in a different place, but those pins basically generate a known signal from the scope through the probe and then back into the scope, so the scope can read itself, if you will. And then it allows you to adjust the signal that the scope sees so that it is exactly like what the scope knows it's putting out on those pins. So this is basically a calibration procedure. And as he said, you're not really going to need to do this very often. When we're reading drive stuff, we're not that precise. We're not doing instrumentation and signaling. So typically, if your probe's a little bit off, it's not going to hurt your ability to analyze the problem. Nevertheless, we do want to use things properly calibrated.
Check
And
that.
Pearson, I jump in there too and mention that he's using a desktop unit. So
Sorry,
Craig. I say, just jump in there to tell him that he's using a desktop unit. So a lot of times we'll use portable units. So
right.
Rather than, we won't have knobs like what he's showing on here. We'll have push buttons that are basically waterproof.
Absolutely, yeah. The unit that I showed earlier, the Fluke scope meter, and I'll show it again, is one of those units that has push buttons very similar to the keypad on the new GA series VFDs from Yaskawa, and they're waterproof. You can spill your coffee on it. I've done it. It takes a pretty good shock. I've also dropped it. And nevertheless, just understand that the functions that he's talking about, the trigger button, the on button, the single button, the channel 1, channel 2 button, they all exist. They're just going to be in different places.
On a rising edge of a signal on channel 1. Most scopes come with some kind of built-in frequency generator, so
back this up a second.
The edge and source is channel 1. Check that slope is set to up edge. These tell the scope that we want to start our measurements on a rising edge of a signal on channel 1. Most scopes come with some kind of built-in frequency generator so you can test your probes and tune the compensation capacitor. This one happens to have a 1 kilohertz square wave generator we can use. Attach the ground clip to the ground tab and hook the probe around the signal tab. You should see something appear on the scope's display. Now, you'll need to adjust the horizontal and vertical scale knobs so you can clearly see the waveform. Note that turning the knobs clockwise decreases the time or voltage scale, which has the effect of zooming in on the waveform. If you want to move the waveform up or down, you can adjust the smaller knob above the channel 1 button. Just note that this moves the 0 volt level for channel 1 as well. If the waveform seems to be moving or jittering, this is because the scope has no idea when on the waveform to start measuring, but we can fix that by adjusting the trigger level. Use the knob in the trigger section to raise the level to somewhere between the min and max of the waveform. This tells the scope to begin measuring as soon as it sees a rising edge, perform one sweep on the screen to draw the waveform, and then repeat the process. Note that digital scopes like this can store and display information before the trigger. Because this is a periodic waveform, the image appears static on the screen. Now, these highs and lows shouldn't appear completely flat, as we assume the scope is outputting a near-perfect square wave. If not, it's because the compensation capacitor in the probe hasn't been tuned, so we're actually measuring the signal incorrectly. Using a tiny flathead screwdriver, adjust the screw head in the probe until the square wave has straight edges. Note that some probes have the compensation adjustment screw near the probe's plug instead. Now that we have everything set up, let's take some measurements. To make some sample waveforms, I've got a mini gen board attached to an Arduino Pro Mini. I can adjust the type of waveform by pressing this button, and adjust the frequency by turning this knob. To start, attach the ground clip to the negative post on the output, and attach the probe tip to the positive post. Just make sure they don't short each other out. Oh, and if you don't have something to clip to, you can usually remove the hook end of most scope probes to get a fine tip that you can press to component leads and traces. Let's take a look at a sine wave. As you can see, we're zoomed in a bit too much on the time scale. Adjust the horizontal scale so we get a clear sine wave. Now, adjust the trigger level to stabilize the waveform. By pressing the measure button, the scope will perform some automatic measuring to give us things like peak-to-peak voltage and the frequency of the waveform. You can also see that there is about a 1.5 volt DC offset on this signal. If you have a non-periodic signal or something the auto-measuring features can't handle, you can use cursors to manually measure waveforms. Press the cursors button and press the top menu button to turn them on. You can measure vertically, which corresponds to voltage in this case, or you can change them to measure time. Select cursor A with the menu button and use the adjustment knob to move the first line. Select cursor B and move it to the point you want to measure. Here, you can see the time between the top and bottom peaks is about 1.16 milliseconds. All of that works great for periodic signals, but what if you have something that only shows up sporadically? For example, whenever I make an adjustment on this knob, the Arduino sends a digital message over SPI to the mini gen board. Let's try to capture that signal. Find an appropriate common line to attach the ground clip and attach the probe to the MOSI line. When we adjust the knob on the breadboard, we can see the message, but it disappears quickly. Since it's not periodic, it's hard to capture in view, so we need to tell the scope to only perform a single sweep once it detects a rising or falling edge, and not keep sampling and drawing on the display. To do that, we first have to set our trigger to falling edge, since this line is normally high and driven low. Set the trigger level to something below the default high voltage. We'll set it to about half the voltage. Now, press the single button, which tells the scope to start measuring once it sees the trigger condition, and to stop measuring after it's made a single sweep across the display. Adjust the frequency knob on the breadboard again, and you'll see our SPI data appear on the scope. You can zoom in, hit the single button again, and recapture the message to measure it and examine the bits to make sure the message looks correct. As mentioned earlier, many scopes have more than one input. Here, I've attached channel 1 to MOSI and channel 2 to SCK, which is the SPI clock. Now, when I do a single-shot capture, I can see how the clock signal lined up with the data bits. And let's say I want to save this image to my computer so I can use it in things like blog posts and lab reports. I can plug in a thumb drive, press the Save Call button, and press Save. Wait for the progress bar to show that it's done writing and pull out the thumb drive.
Now, the procedure that he just went through, I'm sure for the uninitiated, is a little bit overwhelming. I'll include the link to this video so you can review it. But basically what he is talking about is using the scope as a tool to capture a random one-time waveform. Why would we do that analyzing drives? Well, interference. If we've got a probe, a pressure sensor, a transducer, whatever, and every once in a while the VFD gives you a I lost the signal fault, or we start to see values on the input that we know can't be correct on a pump that we know can only produce 60 psi with X number of valves open. The feedback from the pressure sensor is telling us 114 psi, so we know that can't be true. What we want to do is we want to take a look at that signal, and there's probably a bunch of noise that's getting induced onto the signal line and adding to the real value, thus telling us that reality is 65 psi plus all the noise, giving us the 114 psi false signal. This one-time capability to see an interrupting signal, a one-time occurring non-periodic signal, is a very important use of the oscilloscope. Think of the oscilloscope as a set of eyes into a world that you can't see, except when you use this tool.
The picture will be saved as a bitmap in the root directory of your thumb drive. There are a few things to consider when buying an oscilloscope, and knowing what the terms mean can help you read the specs. The first is bandwidth. This is the maximum frequency range that the scope can accurately measure.
What that means is how many times a second the scope can take a measurement. And as we said earlier, it's really difficult for a human to take a measurement every signal and write it down with a digital voltometer, but the scope can do that millions of times a second. It's that fast. So that's the bandwidth.
The problem is that as you go up in frequencies, the amplitude of your signal gets attenuated up to about 30% by the time you reach the listed max frequency. To accurately represent a sine wave, it's recommended that you choose a scope with a rated bandwidth at least 5 times the maximum frequency you intend to measure. Most entry-level scopes have a bandwidth of around 100 megahertz, which means they can really only accurately show sine waves of about 20 megahertz, which is about 2% amplitude attenuation.
Now, 100 megahertz scope is just fine for VFDs reading the output, because what is the frequency of our output? Well, the frequency of our output in the worst case is 15 kilohertz, 15,000 times a second. So if you follow his rule and multiply that by 5, let's just multiply by 10. Math's easier. You're at, instead of 15,000 times a second, you're at 150,000 times a second, which is 150 kilohertz, which is less than 1 megahertz. The scope is 100 megahertz. So you got plenty of bandwidth to deal with the speed of the signals that we're looking at on the output of a VFD.
If you're analyzing digital signals, you'll probably be looking at sharp edges as the signal goes from low to high and high to low. The rise time rating represents the scope's ability to draw details in fast transitions. It's related to bandwidth, and much like the bandwidth rating, it's recommended that your expected signal's rise time be 5 times that of the scope's listed rise time. Digital scopes need to sample a signal many times per second in order to draw it on the display, and the sample rate is the number of times per second a signal is read. Entry-level scopes will generally have around 1 to 2 gigasamples per second. Here, we see the rule of 5 times again. To get a good reading, it's recommended that you pick a scope with a sample rate of at least 5 times your expected highest frequency.
Here again, a 100 megahertz scope, and it's hard to buy a scope nowadays that has less than 100 megahertz capability or bandwidth. It's going to be more than enough to read the sine wave. You want to get multiple points on the sine wave. This is actually a pretty cool way of understanding the sampling rate and what an oscilloscope can do for you. Because if this is the sine wave that you're trying to measure, and you make a point here and a point here, and you don't know anything about what's in between, then this is what you're going to think reality is. Similarly, if we have slightly more resolution, signal data or data per second, we get this, which starts to look a little bit more like reality, but I'm sorry, that's just not it. I want this. I want to look at that, and that's what a scope gives me because it's doing it millions of times a second. Here, we get something that sort of looks like the sine wave we're reading. This is what you get with the tool that can read the data reality millions and millions of times a second.
Resolution refers to the number of bits used to measure and quantify each sample. The more bits, the more precise each sampling will be. While there are other specifications you should consider when looking at scopes, such as probe impedance and auto-measuring capabilities, these 4 should really get you started. Scopes can be quite pricey, but there are alternatives. For example, USB scopes are nice because they are portable and they get the job done about 90% of the time. That being said, if you want to make it look like you're doing something sciencey whenever somebody walks by, all you got to do is just measure a sine wave.
Okay, so the last thing that he mentioned before that sort of lame joke was he pulled that thing out of his pocket. It's a USB scope. I want to point out that the Drive Wizard makes your laptop into a scope, albeit with a very low bandwidth. Yet, the Drive Wizard, with its low bandwidth, its low sampling rate, is just fine for reading most of the data we're trying to trend on a VFD. As opposed to digital signals on a circuit board and with a microprocessor-based circuit board like that Arduino processor that he was looking at earlier, stuff just doesn't happen that fast in our world of analyzing VFDs and pressure transducer signals and other analog signals, what have you. The fastest thing we're going to be looking at are voltage spikes and the interruptions, you know, the little gremlins that we're trying to find that mess up our world. And even those are not going to be that fast in our world. So what I'm trying to do is put this in perspective. For using a VFD or an oscilloscope on a VFD, 100 megahertz scope with a 10 times probe is really all you're going to need. And you're going to be able to read all the signals just fine. And the scope is going to have enough resolution and enough bandwidth to deal with anything that we throw at it in the VFD troubleshooting arena. Okay, I'm going to dump out of this because we've been talking so far about voltage measurement, but we also want to measure current, and we want to measure current fast also. Again, not as fast as a 100 megahertz scope can do, so we're well within the capability of the scope, but we want to measure current as well as voltage. The fact is that our voltages may look great and the motor's not operating properly, and it may lie in, we may be able to uncover the source of the problem by looking at the current waveform as well as the voltage waveform. That's why scopes have more than one input. You can take two signals at the same time, display them on the screen, overlay them on the screen to see visually how they relate. And the typical thing you're going to do with the VFD is you're going to take the voltage waveform and you're going to overlay it on the current waveform so you can see what's happening to the current at the same time as the voltage, and that tells us the story in most cases about how the motor is operating. So the next discussion is going to be on current probes, and it's a little 6-minute video that we'll watch.
Oscilloscopes are typically used to measure voltage, but what you may not know is that you can just as easily measure current with a scope. Hi, I'm Allie. To measure current with an oscilloscope, you have a few options. You can use the Ohm's law method to measure the voltage drop across a shunt resistor. You can use this voltage and your known resistance to calculate current. This is a nice quick way to measure current, but it requires you to do some math in your head to interpret the waveform. And this can get pretty confusing if you have to document your waveform and share it with others. And depending on the shunt resistor you use, it can also introduce extra uncertainty into your measurements. For more accurate measurements, use a current probe. With a current probe, you'll get the measurement in amps right on your scope screen, no calculations required. There are 3 situations where you'll need to measure current. If you're working with really high currents, really low currents, or something in between. And each one of these situations calls for a different measurement strategy. Let's start with how to measure high current. And when I say high current, I mean high current, as in hundreds or thousands of amps. You'll often run into large currents like this when measuring the startup of a device or the switching of a switch mode power supply. A Rogowski coil current probe can measure high currents because it uses an air core instead of a traditional metal core. And with a metal core, we'd have to worry about too high of a current saturating it. But with air, we don't have to worry about that. When current is detected, the Rogowski coil produces a voltage that is proportional to the rate of change, or derivative, of the current that's enclosed by that coil loop. The voltage is then integrated, and this allows the probe to provide an output voltage that's proportional to the input current that you're measuring. Rogowski coil probes have been getting a lot of attention with engineers because they're really easy to use. The probe head is just a flexible loop that you can bend and loop around any component that you want to test.
So what she's talking about is measuring one lead going to the motor so that you can get a current waveform over time. You would connect that to channel 2. The voltage probe you would hook up between that phase that you're measuring and another phase, not ground. And then you can overlay the voltage signal and the current signal and get a really good idea of what's going on dynamically in the motor. You can see it's very easy to connect, it's safe. All we're doing is looping a wire around one of the motor conductors. Now, to put these things in perspective, these probes can get a little expensive. You know, you're talking about $100 to a few $100 for these current probes. The voltage probes, again, you know, $50 to $150. Now, most scopes come with voltage probes. The current probes, typically you're going to have to buy those separately.
Now let's talk about how to measure currents in that in-between range, somewhere between 10 milliamps and 30 amps. For these measurements, most engineers are using a clamp-on style current probe, also known as a magnetic core current probe. These clamp-on style current probes are often used to measure current consumption of things like high-frequency digital circuits, ICs, and power supplies. When you're doing this type of testing, it's often important to get accurate, low-level measurements, which means you need a probe with high sensitivity and low noise. One thing to note is that clamp-on probes are really easy to use. All you have to do is clamp it around a wire, and you're ready to start measuring. There's no extra components or accessories necessary. And these clamp-on style current probes have a hybrid AC-DC measurement technology, which means that they have both a Hall effect sensory element for measuring low-frequency DC contents and a current transformer for measuring those AC contents. So you're able to account for the DC offset of your signal instead of the probe blocking it out. Let's look at an example. I have a couple different clamp-on style current probes plugged into channel 1 and 2. Let's just take a look at the baseline noise of these two probes. On channel 1, I have an older Keysight probe that has a 10-to-1 conversion factor. This means that we're only able to go down to 10 milliamps per division on the vertical setting. And this really isn't good enough for most low-level current measurements. But with the probe on channel 2, we can actually go down to 1 milliamp per division. And with this high sensitivity, we can measure low-level currents with much more accuracy. I've also set up peak-to-peak measurements so we can compare the two probes' baseline noise. And you'll notice that the probe on channel 2 is giving us about 5 to 6 times less noise than the probe on channel 1. With this increased sensitivity and lower noise, we're going to be able to make more accurate measurements. So when you go to pick a clamp-on style current probe, make sure you choose one with an appropriate noise level for the measurements you need to make. This is especially important if you care about signal detail. So let's look at an example. If you're working with something like this CAN bus that I have on screen here, you can start to see how the noise level of your current probe can really affect your measurements. With the older current probe on channel 1, we can barely make out the edge crossings of this CAN bus. With the newer probe on channel 2, we can clearly define all of the bits and make more accurate measurements. Generally, clamp-on current probes don't have much bandwidth, but the current probe we're using on channel 2, the N7026A, has the highest bandwidth available at 150 megahertz. The third type of current measurement is low current, and when I say low current, I mean in the microamp to amp range. Measuring low-level current like this is often necessary when testing things like battery-powered devices, charging devices, or memory chips. Engineers are always looking for ways to maximize the battery life of their devices.
This would be the measurements that we would do on 4 to 20 milliamp signals coming out of a transducer.
And to do this, you need to be able to accurately test your device's low current states so that you can optimize power consumption. To get this level of sensitivity, use a high sensitivity current probe that allows you to measure these low signals with very low noise while maintaining a high enough dynamic range that covers the input signal. So if we look at an example, on channel 2, I have that clamp-on current probe we were looking at before, and on channel 3, a high sensitivity current probe. The true signal that we're measuring is 6 milliamps, and we're getting almost exactly that with the high sensitivity current probe because there's barely any noise from the probe riding on the signal. These high sensitivity current probes are optimized to measure current flow within a DUT to characterize sub-circuits. And this allows both large signals and small details on fast and wide dynamic range current waveforms.
So basically what she's saying is, there's 3 different probes depending on the current level that you're going to be measuring. And if you look over on her scope screen, this waveform appears to be much larger than this waveform, but they're measuring the same signal. The fuzziness around the base signal, which is basically this, which is this, is all the noise that the sensor is adding in. So the sensor's not reading reality correctly. So selecting the correct probe is very important in terms of getting an accurate picture of the signal. Now, there's a scientific principle that I can't remember the name of that says that anything you measure will be slightly distorted by the method that you measure it, because you have to affect what you're measuring in order to be able to measure it. This is a good example of this, and choosing the probe that affects the signal least in delivering that data to the screen on the scope is very important. So current probes, in my opinion, you would outfit yourself with a Rogowski coil, and I would still use the clamp-on for most stuff, and if you can afford it, buy the milliamp probe as well. You're now talking, you're now in the $600 range in terms of equipment, and you've already spent $3,000 on the scope, so you got to kind of bear that in mind.
Yeah. I want to inject something, Pierce, if I may.
Yes, please.
We have meters out there that have the ability to defeat the root mean square function, because root mean square means basically it averages out your signal. So if you've got a system that is giving you infrequent or random spikes, you need to disable root mean square, and so you can see the actual spikes coming in when you're recording.
Yeah, very true. For example, if I'm trying to determine whether my pressure transducer is operating correctly or not, and I'm getting a fault from the drive telling me something's wrong, the typical knee-jerk reaction is, well, just replace the sensor and see what happens. And that's fine if that's the most economic path and you happen to have another sensor in your pocket. However, it may be very expensive to replace that sensor. You may not have another sensor available and you need to pump water. So the scope gives you the ability to do that, and understanding the correct probe is very important. You may find out that your sensor is just fine and the wiring is a little bit off and you're getting too much signal attenuation because of interference from the VFD leads, for example. We've already talked about best practices and how to wire things up. We'll probably run that session again, or maybe I'll just send out that best practices PowerPoint to remind everybody. But that can avoid having to replace hardware in the field because you identify not the sensor being bad, but the wiring is affecting the signal. So.
And often when you're doing current testing, you need to be able to make low-level current measurements while still being able to analyze those larger currents. And to do this, you have two options. First, you can double probe your signal, but this will double probe loading and give you an inaccurate view of your signal. The other option is to use a two-channel high-sensitivity current probe like this one. Making more accurate current measurements starts with the right probe. For more information on how to pick a probe for your measurements, check out the selection guide that's linked below. And for even more probing resources, make sure you download the probe training link below and subscribe to our YouTube channel for more videos like this. I'm Al with Keysight Technologies, and I'll see you next time.
Okay. So in the final few minutes that we have, oh, hold on a second. I didn't turn that off properly. Now I gotta find it. Bear with me just 1 second. Okay. Off. So, let me stop sharing the screen.
Was that Bravin saying mean things about me?
What'd you say?
I was just saying, was that Bravin saying mean things about me? I'm just kidding.
Oh, okay. So, we've basically talked about just some very rudimentary issues in using an oscilloscope, and yet what we've gone over today is all you really need to know to use the scope effectively out in the field. I'll publish this recording, and I will also send you the links to those videos, and I will also send you the data on the scope that we at Yaskawa use in the field, and try to give you some rough ideas of what the costs are associated with it, so you can decide whether you want to either invest in it or rent it when you need it. Certainly, you know, when we come to the field, or when you hire one of our authorized service providers, they're going to come with this type of equipment. In the last few minutes, I want to basically go over that toolkit that you get when you bring one of our service technicians to the field. He's obviously going to show up with a digital volt DVOM, digital volt ohm meter, and the field survivable oscilloscope, the scope meter. He's also going to show up with a megger and, in some cases, even a surge tester. These four devices are the tools that we need to fully flesh out a situation in the field and make correct decisions before we spend a bunch of money running around in circles tearing our hair out. I tend to get into those circular dances when I don't have good data. Certainly, if I'm dealing with a customer that has these devices and knows how to use them, well, you tell me what you're seeing, and I can solve your problem on the phone. And that's, obviously ideal. We want to get to the point where we solve the problem as quickly as possible. So that's pretty much what we've been talking about today. The tools necessary to reduce the time to solve a problem. And most importantly, to solve it accurately. When you look at the costing associated with that, you're probably talking about, again, $4,000 when you're all done for all the scopes and probes you need. Digital volt ohm meter, if you get a good one, is going to be $300-400. A megger, another $300. The surge tester is on the cost scale of an oscilloscope. And by the way, a megger is an instantaneous voltage test that basically puts a high voltage one time into a motor winding, and you're measuring that to ground to see if you get any leakage. That voltage should not show up on ground. That's what a megger does. Bang, one time. The surge tester is basically a voltage insertion device used to test motor insulation that inserts a voltage over time, not just one pulse. So it stresses the winding in a different way and gives you a much better picture of whether that winding is breaking down. A megger will see some things, but not all things. And a megger and a surge tester pretty much will give you the complete picture. By the way, when you use a megger and a surge tester, disconnect the leads from the drive if you don't want to blow up the drive. So, that brings us to the end of this class. I hope that it's been a little bit useful. Main purpose here is to reduce your fear factor, if you will, in using an oscilloscope. And eventually the goal is to become as familiar with an oscilloscope as you are with your digital volt ohm meter, and I can tell you that that is not a long path to take. Once you get a scope in your hands and you remind yourself by watching a couple of these videos, you can become very confident in the use of a scope. For those of you that want to use an oscilloscope and really get some field experience with it, let me know, and the next time I'm in your area, I will bring the scope with me and we can go out and measure some signals. Once you get that familiarity, you will be able to use the tool yourself. So with that, we come to another session end on a Wednesday. Thank you very much for attending. I will send this video out with the links, and it's 8 o'clock, time to go to work. Thank you very much, and we'll see you next week.
Thank you, Pierce.